Okay, tic-tac-beta. Next few questions are about a game called tic-tac-beta. Tic-tac-beta is similar to tic-tac-alpha, but there's several twists. Your marker starts in a random square, but the goal is still always in the bottom right corner. You can move your marker to a square that is previously occupied. You may not move your marker. I'll keep track of occupied squares in my example below by coloring them blue. It's no longer just to keep playing until you win game. The game always ends after a maximum of 8 moves, and your score is as follows. You get 10 points if you get to the goal. You lose a point for every move that you make, so you can have a negative score. And yes, your max possible score does vary depending on where your marker starts. Okay, so important note, depending on your screen size, you may need to scroll right. Fine. So here's an example. So I go down and right, and I win. And the score is 10 for getting to the goal, minus 1, 2, 3 moves. So that's how, okay, that makes sense. This takes a little bit longer, so they go up, left, down, down, right, right. So that should be 10. And then they made 1, 2, 3, 4, 5, 6 moves. So 10 minus 6 is 4. Good. And here's the dumb play, right? So they go 1, right, down, down, left, up, and they're stuck, and they get a score of, they moved 1, 2, 3, 4, 5, negative 5. All right. So how large is the state space for the tic-tac-beta game? How many states do you need to fully represent tic-tac-beta as a state space search problem? Justify your answer. So let me draw some stuff on my tablet, and then I will, so that you understand what I'm doing, and then I'll write an answer. So there's a bunch of different ways to think about this problem, and I pretty much gave credit for anybody who made a state space that had a reasonable number of states that included all the possible states, and it was okay with me if you included some extra states that might not be possible. So for example, some people said the answer was 3 to the 9th power, right? Because what they said is every single square, if you pick any old square, right, there's 3 different possibilities for that square, right? That square could be white, right? That square could have a smiley in it, or that square could be colored in blue, right? And so there's 9 of these, so you end up with 3 to the 9th. Some people said, actually, no, it's not 3 to the 9th, it's 3 to the 8th for all of these guys, because they each have 3 options, but this one only has 2 options because you can't have it blue, because once the smiley gets there, so it wins, so it could only be white or smiley, so they say it would be 3 to the 8th times 2, right? Another thing that, another way people did was they said, okay, well, let me start by thinking about where the player could be. Okay, so the player can be in any of 9 spots, right? And every other spot is either blue or white. So we figure out where the player is. Maybe the player is here. And all of the other spots are either blue or white. So we have 9 choices for where the player goes, and then we have 8 other choices that have to be either blue or white. So that would be times 2 to the 8th. But of course, some people said, oh no, wait a minute, the goal is always white. So then they said, no, it's 9 times 2 to the 7th, right? So that was another way of doing it. What else did people do? Okay. So some people said 9 factorial, right? Because they said you have 9 choices for where the agent starts, right? And then after the agent makes a move, right, the space behind him is going to be blue by default. So the 9, and then, people said, well, this 9 factorial assumes that once you're in a particular space, you have 8 choices to go to. That's not, that's not really true because the problem doesn't let you use diagonals, right? So there's fewer than 8. But But if you say I could move the smiley from here to anywhere else, then the next state is always going to be, you're going to have 8 choices of where to move from there, and this one's going to have to be blue, right? And so on. So that gave us 9 factorial. Some people, what do we got? I think maybe I've covered most of it. Yeah, in any event, if you gave me any examples like that and you said, here's how it works, I would accept that. So, how large is the state space? It's just how you thought about it, right? You could say, you could say it's 3 to the 9th power because each square can be blue, white, or smiley, and there are 9 squares. And that would have been fine, right? I would give you full credit for that. I would be happier if you said it's 3 to the 8th power because each square can be blue, white, or smiley, because each square other than the goal can be blue, white, or smiley, and the goal can just be white, or smiley. So that is 3 to the 8th power times 2, and maybe, can we do superscript in here? We can. So it's 3 to the 8th times 2. And we do a superscript. Because each square other than the goal can be blue, white, or smiley. And the goal can be just white or smiley. All right, so that would have been a perfectly fine answer, but any of the other examples that I gave you too.